Welcome to part 2 of a 5-part R&A's deep dive series,
The Genesis Project, creating an e-commerce site.
The Ghost in the Machine.
Yeah, and it is quite the ghost, honestly.
It really is.
Yeah.
So, as the original researchers behind this project, we are taking you behind the curtain of what we call the persistence layer today.
Right, because our overarching goal here is to uncover the absolute necessity of business continuity.
Exactly. We want to show you why losing data is just, well, it's a fatal event for any startup. We aren't just talking about building an app here.
No, not at all.
We're talking about the underlying mechanics of survival. So I'll be breaking down the technical frameworks building this e-commerce network.
And I'll be handling the systems implications. Specifically, the magnetic and electronic physics that actually keep a digital business alive under catastrophic conditions.
Okay, let's unpack this. Because to get us started, before we can even begin to worry about saving a customer's payment data or managing inventory, we have to look at how a complex network actually wakes up from a cold state.
A cold boot.
Yeah.
Exactly. Picture a massive server rack in a hyperscale data center. When the power is entirely cut, that machine is amnesiac.
Completely blank.
It's essentially just a very expensive, incredibly heavy stack of cold metal, silicon, and plastic. It has no operating system.
None.
It has no memory of what it is, what its job is, or how to talk to the rest of the network. So it requires a non-volatile seed just to wake the central processing unit.
Right.
In our architecture, this is the BIOS, residing in the ROM layer read-only memory.
And the physics of that initial wake-up call are critical. Read-only memory is hardwired at the factory level.
Literally burned in.
Literally. The data is burned into the physical circuitry of the chip. It doesn't need an active flowing electrical current to remember its instructions.
Which is incredibly important.
It is, because when you hit the power button, the CPU wakes up completely blind to the world. It goes straight to that specific physical ROM chip just to pull its very first set of instructions on how to boot up the rest of the hardware. Right, but once the operating system loads and the system is actually running, we cross into a massive architectural chasm. This is what we define as the volatility divide.
The volatility divide.
So if you're designing systems, you probably already know the basics here. Primary memory, or RAM, is entirely electrical, it's incredibly fast, and completely temporary.
Yes.
While secondary storage, like your enterprise solid-state drives or magnetic hard drives, well, that's permanent and high capacity.
Right.
RAM is basically like a frantic whiteboard that gets wiped clean the exact second the lights go out.
Oh, I like that analogy.
Thanks. While secondary storage is the heavy, locked filing cabinet down in the basement. But the friction here is why we have to architect our entire business around this divide. We can't just treat RAM like a permanent workspace.
No, you absolutely cannot. And the reason for that really comes down to the electronic physics of DRAM, or dynamic RAM.
Okay, how so?
Well, DRAM stores your customer's active data using microscopic capacitors. Think of these capacitors as tiny, inherently leaky buckets holding electrical charges.
Wait, leaky buckets.
Yeah, leaky. Because they constantly leak their charge into the surrounding silicon, the system actually has to refresh them with a new pulse of electricity millions of times every single second.
Millions of times a second, wow.
Every single second. That constant refreshing is the dynamic part of DRAM. If that electrical pulse stops, even for a fraction of a millisecond.
The bucket empties?
Exactly. The bucket empties. The data doesn't corrupt. It doesn't get misplaced. It simply ceases to exist.
It just vanishes.
Entirely. Secondary storage, however, relies on states that persist without any power at all. A magnetic drive physically flips magnetic polarities on a metal platter.
Right.
And solid-state drives trap actual electrons inside isolated floating gate transistors. Once they are locked in, they stay locked in.
But hold on. If DRAM is this volatile, this fragile and massively expensive per gigabyte compared to flash storage, why are we feeding the CPU with it at all?
That's a fair question.
Right. Why doesn't the processor just talk directly to the permanent solid-state drives where the data is actually safe from the start?
It entirely comes down to the speed of light and electrical resistance.
Okay.
A modern enterprise CPU operates at billions of cycles per second. It is moving so incredibly fast that if it had to wait for a physical hard drive to spin to the right sector, or even for an SSD to push electrons through a gate, well...
It would just be waiting around.
Right. The CPU would spend 99% of its life just waiting. It would be starved for data.
Ah, I see.
So RAM is positioned physically closer to the CPU on the motherboard. And because it relies on those lightning-fast electrical refreshes rather than permanent physical state changes, it can keep the processor fed at the exact speed it requires.
So the extreme volatility of the system is just the mandatory price we pay for speed.
Exactly. You have to pay that tax.
So what does this all mean for the business? Because it leads directly into our first major architectural friction point.
The blackout scenario.
Yes, the blackout stress test. We have this physical chasm between temporary electrical speed and permanent physical magnetism. So let's run the test.
Okay, set the scene.
You are a customer on our new platform. You've loaded up your cart. You hit checkout, and you submit your payment payload. That data leaves your device, travels across the internet, and hits our server's active memory. And at that exact millisecond, before the database transaction finishes, the power grid fails.
Oh, from a systems perspective, that is a terrifying sequence of events.
Right.
Yeah, because if that customer's credit card payload is sitting purely in the server's DRAM when the voltage drops, those leaky buckets empty instantly.
Gone.
The entire state of that transaction vanishes into thin air.
And think about the cascading business consequences of that vanishing act. From the customer's perspective, their app might just be hanging.
Or they get a vague browser timeout error.
Right. And then they're wondering, did the payment clear the gateway? Did we charge their card but lose the internal order record?
Which is a nightmare.
Total nightmare. Now you have support tickets flooding in, chargebacks hitting your merchant account, and an immediate loss of consumer trust. For a startup trying to gain market share, a data loss event like that is fatal.
Absolutely fatal. What's fascinating here is how systems design has to aggressively compensate for this physical vulnerability.
Because you can't just hope the power stays on.
No, you definitely can't. This introduces what we established in the architecture as the mandate for persistence.
The mandate for persistence.
Right. As the designers of this platform, we have to enforce a strict, immutable rule within the codebase.
Okay.
From a business continuity standpoint, the system must commit the write function to a magnetic or flash substrate, meaning non-volatile secondary storage, before it is ever allowed to send the customer an order confirmed message.
Wow, okay.
We cannot send that success status back to their browser until the data is physically locked in a state that will survive a blackout.
But wait, if we force the CPU to insert this mandatory pause, making a Ferrari-level processor stop its high-speed electrical calculations in RAM just to physically commit data to a slower drive down in the storage array.
Yes.
Aren't we intentionally bottlenecking our own application? Doesn't that mandatory synchronous write slow down the checkout experience for the user?
Well, it absolutely creates a bottleneck, but it is a non-negotiable one.
Okay.
We are intentionally sacrificing a fraction of a second of application speed for an ironclad guarantee of survival. Designing an enterprise system isn't just about maximizing speed at all costs.
It's about managing catastrophic risk.
Exactly. We can aggressively optimize everything else on the platform. We use massive content delivery networks for image loading. We optimize the front-end user interface. We cache the search functions so they are instantaneous.
But the transaction itself has to be secure.
Right. The actual moment of transaction, the financial exchange, and the inventory deduction must be synchronous with permanent physical storage.
Okay, so we've established why data must be written permanently to survive a disaster. But simply surviving a blackout isn't the end goal, right?
No, you have to actually run the business.
Exactly, and run it at a massive scale.
Yeah.
And that brings us to the architecture of how we actually retrieve that saved data when thousands of people are using the site at once.
The access method wars.
Yes, the battle between SASD and DASD.
Right. Those acronyms basically define the mechanical reality of how data is retrieved from a physical medium. SSD stands for Sequential Access Storage Devices, the classic enterprise example being magnetic tape backup. And DASD stands for Direct Access Storage Devices, which encompasses your standard hard disk drives and modern solid-state arrays.
Here's where it gets really interesting. To understand why this distinction dictates whether an e-commerce platform scales or dies, let's look at this SD nightmare scenario.
Oh, the nightmare, yeah.
Imagine if our live customer database were stored on sequential magnetic tape. You log into your account and decide you want to update your shipping address. You hit Edit Profile. If we were running on SASD, the storage controller would have to start at the very beginning of the physical tape spool and literally reel and spin through the records of every single customer who ever signed up before you.
It is staggering to think about.
Mechanically, reading past user number 1, user number 2, spooling hundreds of feet of tape just to find your specific data block.
Right. And sequential access is highly efficient if
Yeah.
you are just doing a master backup of the entire database at the end of the night. Taking a complete linear snapshot.
Sure.
But for a live, interactive e-commerce environment where 10,000 users are requesting their unique data at random intervals, a sequential system would cause the entire application to grind to a halt.
The mechanical queuing delay alone would crash the server.
Instantly.
It's basically the difference between trying to scale a business on VHS versus streaming.
Oh, that's a perfect way to look at it.
Right. On a VHS tape, you can't just jump to an hour into the movie. You have to mechanically fast forward and spool the physical medium over the playheads.
Yeah.
DASD, direct access, is the streaming model. You click a timestamp and you're instantly there. But in a database context, we aren't just skipping chapters in a movie. We are jumping straight to a specific, unique account ID out of millions of active records.
And the underlying mechanics of direct access are what make that instant retrieval mathematically possible.
How does it do it?
A DASD system organizes data into highly specific physical addresses, cylinders, tracks, and sectors on a hard drive, or specific electrical cell blocks on a solid-state drive.
Okay.
So when you click Edit Profile, the database index looks up your unique account ID, translates it into exact physical coordinates, and moves the read head directly to that precise location.
So it entirely bypasses the petabytes of data sitting before and after it.
Entirely. DASD is the only viable way to scale a modern network.
But, even with incredibly fast direct access storage, we still face a massive synchronization problem between the different architectural components of our server.
We do.
And this introduces a critical systems engineering concept we call the CPU idling tax.
The idling tax, yeah.
This is the logic of how slow storage operations, which we refer to as I/O or input-output, can actively starve a high-speed processor. Think of it this way. We spend top dollar equipping our server racks with absolute powerhouse processors.
Yeah.
We are paying for a Ferrari or an ultra-fast automated factory assembly line.
Right.
It wants to process millions of calculations a second. But when the CPU needs to retrieve a complex product matrix from the storage drive, it has to send a request and wait.
That just sits there.
Yeah. If that disk drive is a mechanical bottleneck, our ultra-fast factory basically has to shut down and wait for a single slow delivery truck to arrive with the parts.
Yes.
The CPU is idling. It is burning expensive clock cycles, wasting potential computing power, doing absolutely nothing while it waits for the data.
And if we connect this to the bigger picture, that I/O hierarchy doesn't just apply to the invisible digital world inside the server rack.
No, it doesn't.
The interplay between processing speed and input-output hardware creates massive ripple effects that extend all the way into the physical reality of our business operations, specifically down on the floor of the shipping warehouse.
Exactly. Because the digital architecture isn't contained in a vacuum. When an order is confirmed on the server, locked into persistence, and processed by the CPU, it eventually has to become a physical cardboard box, leaving on a freight truck.
And to make that physical transition happen efficiently, we have to look at the physical output hardware deployed in the fulfillment center.
Okay.
In warehouse systems design, we draw a clear line between impact and non-impact hardware.
Impact and non-impact.
Yeah. You might logically assume that for a cutting-edge e-commerce platform, we would deploy the fastest, quietest, most modern printing technology at every single workstation.
Well, yeah, wouldn't we?
For customer-facing collateral, the glossy packing slips, the promotional inserts, we do exactly that. We use non-impact hardware like high-speed commercial laser or inkjet printers.
Right.
They are incredibly fast, silent on the floor, and they produce beautiful, high-resolution text by silently melting toner onto the paper or spraying microscopic drops of ink.
But wait, if we are optimizing this entire platform for speed and efficiency, from the solid-state drives all the way to the packing slips, why would we deliberately choose to install old-school, incredibly loud, clunky impact dot matrix printers anywhere in a modern fulfillment center?
It seems crazy, right?
Doesn't relying on 1980s mechanical printer technology completely contradict the whole Ferrari CPU efficiency model we just spent the last 10 minutes establishing?
It seems like a massive technological regression until you factor in the physics of business continuity.
Okay, explain that.
Dot matrix printers are impact hardware. They operate by firing tiny metal pins physically through an ink ribbon, striking the paper with actual kinetic force.
And why does kinetic force matter?
Because of carbon copies. When a massive pallet of our products is loaded onto a third-party freight truck, the driver and the entire downstream logistics network require permanent, multi-part carbon copy shipping manifests.
Oh, I see.
A modern laser printer cannot create a carbon copy because it relies on heat and static electricity, not physical force.
Wow.
The kinetic stripe of the dot matrix printer's pins transfers the exact same information through 3 or 4 layers of chemically treated paper simultaneously. You get a master copy, a verifiable copy for the driver, and a hard copy for the warehouse records, all generated in a single physically verifiable pass.
That is incredible. So physical kinetic redundancy actually trumps digital speed the very second that freight truck leaves the loading dock.
Precisely. In comprehensive systems design, the most advanced, frictionless digital architecture in the world still has to interface with the messy physical reality of logistics.
Right.
And it's not just the output hardware that bridges this gap. The input ergonomics of the warehouse are just as vital to the system's survival.
How so?
Well, when we say input device, most people immediately picture a mechanical keyboard and a mouse. But in a fast-paced warehouse environment, a forklift driver doesn't have the time or the physical ability to type a 16-digit alphanumeric tracking number into a terminal while holding a 50-pound box.
Right, which means the physical environment requires an entirely different sensory apparatus.
Yes.
The handheld scanners, the wireless RFID readers, and the automated weight sensors built into the conveyor belts become the literal nervous system of the warehouse.
They really do.
They bypass the keyboard entirely. They are constantly sweeping barcodes, sensing directional movement, and firing millions of tiny data points back up the chain to the servers. They update the centralized inventory in real time, feeding that digital architecture without a human ever touching a traditional input device.
This raises an important question, though.
What's that?
If those scanners and sensors are the nervous system of our e-commerce warehouse, continuously firing a massive stream of behavioral data back to the server, and our storage drives are the permanent memory of the organization, what happens when the system generates so much data? Every single scan, every forklift movement, every micro delay on the warehouse floor, that deciding what not to store becomes the ultimate survival skill for a startup.
Oh, wow. Yeah, deciding what to actually throw away.
Exactly. Thank you for joining us, and we look forward to continuing this journey with you.
Keep exploring. Expand your mind.